Thanks for the introduction. So I'd like to, for the next 20 minutes or so, tell you a little bit about new models for random oracles, new security models for random oracles, and some work I've been doing with Arno Mittelbach while he used to be at Darmstadt. Okay, so we all know that random oracles are very useful objects in cryptography, and random oracles model ideal hash functions. So in the random oracle model, we have a setting where all parties have access to a uniformly chosen random function from a set of all functions. That is the random oracle. And I'm sure you know that random oracles enable security proofs of many cryptographic protocols out there, such as encryptions and signatures, key exchange protocol, disk encryption, where you need key-dependent message security, for example, et cetera, et cetera. But even though they are very useful, reliance on them have become a little debatable since the 90s. And this is because of a result of Canetti, Goldreich, and Halevi from 98, showing that there are uninstantiable random oracle model schemes. So what does that mean? So that means that I can have an encryption scheme ENC with access to some oracle, such that ENC, when run with a random oracle, is secure. But when I run ENC with a hash function, it becomes insecure for any hash function. So, and on top of this result, there also has been a lack of definition formalizing what random oracle behavior is. So you might say, well, let's just start looking at a very simple definition for what it means to be indistinguishable from a random oracle. That's how we go about defining security models in cryptography. So we call a hash function indrow, indistinguishable from random oracle, if over a random choice of a hash key, if I run the adversary A on the hash key and give it access to a box, which either has the hash function with the hash key or the random oracle, it cannot guess whether it was talking to the hash function or the random oracle. Yep. So the adversary is talking to either the hash function or random oracle and needs to tell which one it is talking to. So the advantage is defined, as usual, by the probability of guessing the bit. So this bit signifies whether you're talking to hash function or random oracle, scaled away from 1/2. So of course, this model is clearly uninstantiable. And the reason for that is very simple. It's because you just compute hash of 0 and compare it to oracle's answer. So you have the hash key. You just compute the hash of 0 and see if it matches what you got from up there. So of course, this naive solution does not work. And it is kind of behind this is the reason that the adversary knows a full query, a full input to the hash function. That is the hash key and the 0 that you end up hashing. So you say that, okay, let's then hide the hash key. If we hide the hash key, then we might get something which is instantiable in the standard. So if you hide the hash key, we end up in this setting where the adversary gets a security parameter. But if you hide the hash key, you actually end up with a notion called PRF security. But this is not so useful in the context of hashing because the hash key is often publicly available. So how about having a kind of a combination of these two ideas? How about splitting A so that one part gets the hash key and the other doesn't get the hash key? So we'll have now two components of the adversary A, which we call the source and the distinguisher. And the setting looks like this. So we have one part of the adversary source, one part of the adversary distinguisher. The source does not get the hash key. It talks to the box. And once it finishes, it sends some leakage to the distinguisher. And the distinguisher has the hash key, and it needs to then decide the bit. So I've just taken the adversary, and I've just split it into two parts. So advantage is defined as usual. But then if you think about it a little, nothing has changed, really. This model is still uninstantiable. It's because you can do the exactly same attack. You just query this box on 0. You send the value over to D, and then D will compute the hash of 0, and then we'll check if it matches the answer that you got from the box. So exactly same attack as before. Okay, so not quite yet over. Yeah, but note that in this attack that I described, that you leak a 0 and hash of 0, one query of this source S gets leaked to the distinguisher. So how about having like another restriction saying that let's restrict L so that it doesn't leak any of the queries of S. Let's see what happens. And if we do that, we get a notion, a recent notion called Universal Computational Extractors, or UCES, by Bellare, Huang, and Kielvidi from Crypto 2013, which basically looks at the setting that we were discussing before, and then formalizes what it means for the leakage L here not to leak any of these values X that are sent into the box. And the way you do that is via this game over here. That is, you run the source S with the random oracle. At some point, the source outputs some leakage L. Then you feed this L to a predictor P. And the requirement is that no predictor should be able to output one of these X primes. So the predictor outputs X primes, such that this X prime is a member of this set of queries over here on input L. So that's basically how you go about defining unpredictability. So how do we define security? So first of all, we say that the source S is unpredictable if the advantage of any predictor against the source in this game is negligible for all efficient predictors P. And then we define UCE security. We say that this hash function H is universal computational extractor secure if the advantage in this game against the source and distinguisher is negligible for any unpredictable S. And unpredictable S was defined over here. So basically, if you talk to a box, and if your query is unpredictable, and then at some point you get the hash key, you get a new sort of security definition which might or might not be feasible. So okay, this is a definition. Is it useful or not? It looks kind of somewhat natural. It turns out it's actually very useful. You can use UCEs to instantiate random oracles in a lot of applications. And examples include deterministic public key encryption, message-locked encryption, related key attacks, and key-dependent message security, point function obfuscation, proofs of storage, et cetera, et cetera. And the takeaway message from this slide is that UCEs basically model many random oracle-like properties for hash functions out there. So the goal of our paper is to basically see how much we can extend these UCEs, to what extent can we model other properties of random oracle-like behavior. So for that, and one of the motivations to do this is that UCEs have a number of shortcomings, and there are three different shortcomings, but they're kind of all interrelated. And one of them is that UCEs are not instantiable with unkeyed hash functions, because the definitions intrinsically has a hash key inside it. And if you remove the hash key, then the definition will no longer work. You can launch trivial attacks on the definition if there is no hash key. And queries are independent of the hash key because the source S does not get the hash key, and yeah. And the model does not allow for adaptive query. Once you pass the leakage from source to D, the D does not get access to the oracle anymore. So the question is can we overcome these? But maybe there's another motivation out there, and it's more of a conceptual motivation, and that is that one way to look at UCEs is that they model the securities of hash functions by looking at random oracles under unpredictable queries. So I'm not trying to say, so the first definition was that we looked at int-row, indistinguishability from random oracle, and the adversary could just query it on any input that it wants. So now let's look at a model where the adversary can talk to a box, which is a hash function random oracle, but the queries are unpredictable. So can we build in this intuition to have a more general framework where we directly try to model this property of being random oracle-like under unpredictable queries? So recall that this was the UCE setting where we had the source and the distinguisher which talk to the box. And the box, now I've written it slightly differently. It has a hash, which is parameterized by this bit B, and it has the hash key hardwired in, which is randomly chosen and is independent of source's view. And then at some point, the distinguisher gets hash key. So if you think about this, the source does not get the hash key. So if you look at the full input of the hash, the full input remains hidden from S's point of view because the hash key is hidden. And then when you come to over here, even though the distinguisher D gets the hash key, unpredictability conditions said that the leakage, L, does not leak any of the queries. So all the X's that go in here remain hidden from distinguisher's point of view. So hash key remains hidden from S's point of view, X remains hidden from D's point of view. That is basically what is really happening behind the UCE definition. So what about the new definition? Well, why not just try to model this directly? Why not have a hash key? Why not have this hash function out there and have two distinguishers which are talking to the hash function, and they can write to the inputs of the hash and get outputs out, and they can talk to each other via this leakage L, which can go from D1 to D2 or D2 to D1, and at some point D2 decides. And the property that we are going to have is basically a generalization of this. We're going to say that all the queries made in this run of the game are hidden from both D1's and D2's point of view. So a little bit more formally, we define unpredictability where we run this game with respect to a random oracle. That is to have a definition of unpredictability which is independent of the choice of the hash function. And then we say that no predictor P should be able to predict a query of D1 or D2. So that is, we give the predictor P the view of DI. So we give it either the view of D1 or D2. And what is this view? This view is basically everything that DI gets. So what are the set of everything that distinguisher DI sees? These are the coins of DI. These are the incoming leakage to DI. That's all the leakages which are passed from D2 to D1, and all the hash values that it sees from the oracle. That's everything that the DI sees. So the requirement is that I give the predictor P the view of the I, and it shouldn't be able to come up with an X such that the X are in the queries of D1 or in queries of D2 for both DI. So this mechanism of two distinguishers being able to talk to a single box allows the distinguishers to make unpredictable queries to the hash function. Because if you consider that there's just one adversary talking to a box, it can never make unpredictable queries. Because an adversary already always knows its queries. It can never make unpredictable. So you need to have at least two. So adversaries. So what can we do with this definition? So recall a very simple encryption scheme of Black-Rogowe-Shrimpton, which is called this BRS encryption scheme, which is kind of the most simple encryption scheme you can imagine. That is, you encrypt message under key on some randomness, where you output randomness, and then you hash the randomness with the key and XOR with the message. And this was shown in the original work to be KDM secure in the random oracle model. And recall that in the KDM security, the adversary gets to see encryptions of f of k under k. So you get to see encryptions of key-dependent messages under k. So here, we establish its RKA, that's related key attack, and KDM security without random oracles. That is using ICEs. By the way, I should have said that going back, that we call these interactive computational extractors, because somehow these two adversaries interact with each other. So in the RKA game, the adversary gets to see encryptions of messages of its choice under related keys, under keys which are derived with some functions f, and hence those keys could be related. So the theorem statement is that this encryption scheme here is RKA secure against split functions. So split functions are functions which basically apply functions in parallel to the left and right of the keys. If this hash function H used in the encryption scheme is ICE secure. And as we'll see, this will also imply that this scheme is RKA secure in the random oracle model. So this will follow from next theorem. So what about full RKA security? This is a little restricted, even though it is wide enough to capture many practical cases, such as XORing with a constant. So if you look at offsets, key offsets, you'll see that it will fall into this template of related key attacks, because you'll just XOR in parallel. Full RKA security. I have to say that in the ICE framework, we can actually formulate many different security notions. It's not one security definition, it's a class of security definitions. And depending on how you go about to formulate these notions, new security definitions emerge, and you can then prove new properties. So what about other applications? So first of all, ICEs are a generalization of the UCE framework, and they can have all applications of UCEs. But we can also do more. So on top of showing adaptive RKA security for split functions for BRS schemes, we can also show what I call a semi-adaptive split KDM security for BRS. So we can't quite get full adaptive KDM security. We can get correlated input hashing and other foundational primitives such as weak PRFs, randomness extractors, one-way functions, as long as they have polynomial regularity, etc. So what about feasibility of these ICEs? One first question is whether ICEs are actually feasible in the random oracle model. I mean, collision-resistant hash functions are feasible in the random oracle model. Are ICEs feasible in the random oracle model? And then you say that, well, why are you considering this question at all? Because the whole point was that we were trying to move away from the random oracle, and now you're going back and considering a random oracle model feasibility. But there are two kind of points for this. And the point is that if you establish such a thing in the variable input length random oracle model, you'll basically establish that that the definition is structurally sound, that there are no generic attacks on the definition. And it also enables a layered approach to security in the protocol analysis. So you can first design a protocol, then analyze it with respect to an ICE, and then finally instantiate